Welcome back. Let's try another example. This time we're integrating first with respect to y. So x will be treated like a constant. So starting out, I'll have the integral from 0 to 1, and now I'm going to evaluate the inner integral. Since 3x is a constant, the antiderivative with respect to y is 3xy, and then I'm going to have minus 1/2 y squared. We're evaluating that from 0 to x squared, and I still have this dx hanging off the end. Let's plug in 0 and x squared. So that'll give me integral from 0 to 1 of 3x times x squared, because the x squareds are going in for the y's. And then I have minus 1/2. Now I've got y squared, but y itself is being replaced by x squared. And then I'm going to have minus 3x times 0 minus 1/2 times 0 squared dx. Let's clean that up before we try to integrate again. So now I have integral from 0 to 1 of 3x cubed minus 1/2 x to the 4th, and the rest of the stuff is zeros. And then the dx. By the way, don't forget to put your dx's and dy's in. They're an essential part of the notation, and your work won't be correct without them. Finding the antiderivative now with respect to x. Let's see, I'm going to have 3/4 x to the 4th minus, I'm going to have an x to the 5th, and I'm going to be then having 1/2 divided by 5. So that's going to be 1/10. And we're evaluating from 0 to 1. By the way, in terms of what I just said about needing the dx's, the dx goes with the integral sign. They're kind of bookending your integrand. So once you've done the integration, they both drop out. But until you've done the integration, they both need to be there. Anyway, plugging in our 1 and our 0, that gives us 3/4 times 1 to the 4th minus 1/10 times 1 to the 5th minus 3/4 times 0 to the 4th minus 1/10 times 0 to the 5th. And of course the stuff in parentheses is just a 0, leaving me 3/4 minus 1/10. So let's see, the LCD for those would be 20. (15/20) minus 2/20, which is 13/20. Now, what region was that integral evaluated over? Let's see, the y's went from 0 to 1. Sorry, the y's went from 0 to x squared, and the x's went from 0 to 1. So the region is the set of xy pairs such that x is between 0 and 1, and y is between 0 and x squared. But that doesn't tell us much more than the limits of integration did. So let's see what that looks like. I think I'll go off to the side. So this you could think of as scratch paper to remind you how it works graphing inequalities that are not linear, such as y is less than or equal to x squared. So what you always do with inequalities is you graph the equality. So I'm going to graph y equals x squared. That's our basic parabola. And the thing you graph by putting the equals in is always going to split up your xy plane into two regions. The region you want and the region you don't. Now in this case, the region we want is the regions where the y's are smaller. All right, that's because it says y is less than or equal to something. So where are y's smaller? Well, they're smaller down below. In other words, as you go down, y's get smaller. So that's the region we want if all we're doing is graphing y is less than or equal to x squared. But of course, we have more going on here than that. So let's get the more going on into the picture. X's being between 0 and 1 means that we are going to be to the right of the y-axis, but to the left of the line x equals 1. So I guess I'm going to just dot that in there. And we're staying to the right of the y-axis. Then the y's are positive. So that means we're going to be above the x-axis. But as we said, we're going to be below the curve y equals x squared. So there is our basic x squared parabola, and we are in the region below that. Yeah, the one thing I should do here, let's see, I've got the scale labeled on my axis, by which I mean I've got ones here so we can see what the scale is. I should really label my axes, x and y. And we also should label this curve, and that is the curve y equals x squared, so that it's clear to someone looking at this graph what this region is that is being graphed.